The bottleneck in 3D generative AI is shifting fast. It's no longer just about making something look right from one view, but keeping geometry, motion, and camera control consistent across time. That matters because once models can trace tracks, fill in what's hidden, and render with far fewer primitives, you get video and 3D systems that are sharper, more editable, and dramatically more efficient. The common thread here is a move from pixel-level guesswork to explicit spatial structure. Keep watching, because the details reveal how close we are to practical, controllable 4D generation. Let's explore the first paper. Track 2, View 4, Deconsistent Camera-Controlled Video Generation via Paired 3D Point Tracks. Track 2 View is a camera-controlled video regeneration framework that targets 4D consistency by conditioning a video diffusion transformer on paired 3D point tracks instead of per-frame camera embeddings or noisy dot-rendered geometry. Built on the WAN2, one video diffusion transformer, it uses a dual-view track conditioner with parameter-free bilinear sampling and scattering, plus an 8-layer temporal aggregation transformer to propagate sparse track information across source and target views while preserving explicit spatial and temporal correspondences. The training pipeline extracts one-to-one paired tracks by running Spatial Tracker v2 on a 161 frame temporally concatenated sequence from the multicam video synthetic dataset, then fine-tunes the model with LoRa rank 64 for 216K optimization steps. On the 400 video RealCam vid benchmark spanning 200 static real estate 10K scenes and 200 dynamic mirror data scenes, Track 2 View sets the best overall camera control and view synchronization results, reaching FID 26.82, Clip V 93.22, and Matte Pix 0 695K at 81 frames, while reducing rotation error by 30-65% and translation error by 61-72% versus leading baselines. It also scores best or second best across all 6 VBench dimensions, indicating that stronger geometric control does not sacrifice perceptual video quality. Let's explore the second paper, World Tracing Generative Pixel Aligned Geometry Beyond the Visible. World Tracing, developed by World Labs and the University of Illinois Urbana-Champaign, reframes image to 3D as a pixel-aligned multi-layer geometry problem. For each input pixel, the model predicts a stack of 6 camera space XYZ intersections, with layer 0 reconstructing the visible surface and deeper layers completing occluded geometry beyond the visible. The system is instantiated as WT-DIT, A1-7B parameter flow matching diffusion transformer built on a frozen Moji VTL encoder, trained with an XYZ-only depth-filling objective, 3-way attention factorization over layer-wise, ray-wise, and global tokens, and a mixed diffusion time schedule that balances reconstruction and generative completion. On held-out object data, WTO reaches 0.0149 MAE and 0.0243 RMSE on visible surface depth, while also improving complete geometry to 0.0213 L1, 0.002 Liki, and 0.898 F at 0.05. On held-out 3D front scenes, WTS posts 0.0102 MAE, 0.0215 RMSE, and 0.9867 F at 0.05 at layer 0, plus 0.0216 all L CDL1 and 0.8951 all L F at 0.05 for full multi-layer geometry. The model also extends to dynamics, achieving a 0.0105 mean CDL2 across OBJ, Val, TrueBone, and ActionBench, and its pixel-aligned representation enables training-free, pose-aware, textured mesh generation, text-driven scene editing, and geometry-conditioned novel view video synthesis. A mixed training ablation on real depth corpora further lifts WTS to 0.0374, ABSREL on NYU, and 0.0332, ABSREL on ETH 3D, indoor, showing that the same multi-layer architecture can absorb single-layer RGBD supervision without sacrificing occluded geometry prediction. Let's explore the third paper, ZipSplat, Fewer Gaussians, Better Splats. ZipSplat, from ETH Zurich and Microsoft with Mark Polyphase as an author, is a feed-forward 3D Gaussian splatting method that breaks the usual 1 Gaussian per pixel design by decoding compact scene tokens into unconstrained 3D Gaussians. A multi-view backbone, instantiated with DA3, Giant, produces visual tokens that are compressed by k-means into scene tokens, refined by cross and self-attention, and decoded by a lightweight MLP into 32 Gaussians per token. A one-directional chamfered geometric loss, depth supervision, coupled initialization, and a progressive view. Compression schedule stabilized free 3D placement. On DL3 DV and Real Estate 10K, Zipsplat reaches state-of-the-art pose-free novel view synthesis, while using about 6 times fewer Gaussians than pixel-aligned baselines, including a 24 times reduction versus DA3 on DL3 DV. It improves over Yonosplat by 2.1 decibels PSNR on DL3 DV and 1.2 decibels on Real Estate 10K, and with test time token optimization, it adds about 5 decibels more PSNR in roughly 3 seconds on a single RTX 4090. The model also generalizes zero-shot to MIP, NERF, 360, and ScanNet++, where its pose-free variant reaches 21.72 and 18.01 PSNR at 32 views respectively, and a post-condition version climbs to 23.49 PSNR on ScanNet++. Because compression is set at inference, one trained model traces a continuous quality efficiency curve. At 192 views, scaled compression reduces storage from about 183 megabytes to 9.3 megabytes and boosts rendering speed from 40 frames per second to 401 frames per second. That's a wrap on today's AI paper highlights. Thanks for watching.